My name is Ray Fusillo. I'm a development lead here at InterSystems. In this talk, I'm going to cover some of the performance and scalability aspects of mirroring. I'm going to go into a little bit of how the software is designed for performance and scalability, and how that relates to system architectural decisions that you can make to ensure that things work optimally. I think it's worth kind of doing a little level set review on what mirroring is and some of the terminology we'll use. Mirroring fundamentally is a technology to provide availability, both for high availability and for disaster recovery. It's based on logical replication, so that you have a replicated environment, no common data shared between the two, between the different systems. It's designed from the get-go, like all of our products, for scalability and throughput. And mirroring provides support for quite a diverse set of system architectures. I'm going to go through and show you some of those. One of the key things that's of interest when thinking about throughput is geographical separation. So that will be a little bit of a focus of this presentation. To describe, we should talk about what a mirror is. A mirror is a set of cache systems. You define mirror members with a given type. That type can be failover or async. A mirror can have one or two failover members. So you define members as failover members, which means they can become primary automatically. You don't define you don't designate which one's going to be primary and which one's going to be backup. That's sort of a transient thing based on the current state of the world. Any failover member, if it's ready to become primary and there is no other primary, it will just go become primary. If you have a second failover member, then it will later join as backup. It will connect to the primary. It'll be a target of a sort of synchronous replication, and it will be able to automatically and rapidly become primary if anything were to fail on the current primary. You can also define async members. You can define them. You can define async if you have a one failover member mirror. You can let that member become primary for the sole purpose of serving other asyncs. But async members can also connect to mirrors that have two failover members. Async members have two main purposes, and this is reflected in their type. You don't just define an async to be a generic async. You define it to be either a disaster recovery member or a reporting member. Disaster recovery members can be manually promoted to a failover member and become primary. So upon making a business decision that you have some disaster that causes your primary and backup to go to be unusable. Maybe it's a data center failure. Maybe it's something smaller. You make a business decision that we are going to switch to the disaster recovery data center or the disaster recovery computer. Once that business decision is made, mirroring makes it incredibly simple and seamless to promote a DR member to a failover member and let it become primary and support production. We also allow reporting async members. Reporting async members can never be promoted. They can't become primary. They're really just there to act as simple replicas of the data for whatever you want to use it for. Offline reporting is one use for it. Deep sea. You can also, reporting members don't need to have all of the mirror data sets so that they can contain only a subset of the data that you care about for reporting. Reporting members can also even write, if you configure it to do so, reporting members can update mirror databases, their local copy of mirror databases. So they can, if you have some reporting task or some some other special task that wants to take a replica copy of the primary data set and make some changes locally, you can do that with reporting members. Any database, once a database has been modified like that, outside of the primary, once it's been modified on a reporting member, no copy of that database can, a copy of that database can't ever be used on a primary or a DR system. So they're really only for, it's only for the reporting system's local use. You can change its type after the fact. However, there's many things you could have done on that reporting system that make it inappropriate for it to be a DR system. So, like, you can do it, but there's a bunch of warnings, and if you were so you can do it basically. The reason we allow you to do it basically is if you made a mistake in defining which type it is. If you really intended it to be a reporting member and you've made it read-write databases, or you decided for it not to have a copy of all the primary databases, if you were to switch it to a DR member, you'd get a bunch of warnings, and it might not be the right thing to do. Mirror configurations are a property of the configuration, the CPF file, the configuration. And all mirror members configs basically have a map of the entire mirror. So all mirror members know about all other mirror members. Okay? I'll take more questions at the end too. I'm happy to talk as much as you want about. I'd like to just take you through a few example diagrams that just sort of describe some of the mirror configurations we think about. You can mix and match, and these aren't the only ones. Please don't get bogged down in the detail. These are all stolen directly from the documentation. So you can look at all these diagrams and more examples in the documentation with complete text descriptions of what all these different components are. I just wanted to kind of give you a general flavor for the type of configurations you might imagine. This is just illustrating a simple failover pair. You can add on, like I said, you can add on async members, DR, or reporting. Here's an example of a mirror that has only one failover member, because mirroring is just used in this case for DR and reporting. For high availability, perhaps the failover member is actually a virtualized, maybe failover member is in a virtualized environment, and VMware HA is providing all of the high availability that this particular site needs. So they really just want mirroring for DR. Or perhaps A is in a sort of classic failover cluster, and the site is would rather use that than failover mirroring. These are all things that can be supported. This is an example of a geographically separated DR system. In this case, fully redundant. A sort of lesser configuration would only have one DR member off in this other data center, but this configuration, this is an example of a configuration where someone wants full HA in their DR data center. So they have two failover members in data center 1. Data center 2 has 2 DR members, and in the event that a disaster occurs and you want to switch to data center 2, the intention here is that both of those would be promoted to be two failover members to provide HA in the alternate data center. Again, you could certainly just have one in the alternate data center and say, hey, if we ever have a DR, if we ever have a disaster in data center 1, we're perfectly willing to not have high availability in the DR data center. But this is meant to be sort of a co-equal data center configuration. We can also do failover between data centers. So you can have failover members that are themselves in separate data centers. We'll talk about some of the performance and scalability implications there. very many applications can be supported in this environment. This is sort of allowing properties of both high availability and the separation, the physical separation that you normally attribute with a DR system, but doing that with only two members, trying to reduce hardware. So that's sort of some example configurations. Now let me give you a little primer on how the software actually works. And it'll be evident why you want to know this, because this actually is directly tells you about what sort of interactions there are in the software that you want the hardware and configuration stuff to optimize. So on the left we have a primary system. We have some users that are happily doing their thing. They're modifying databases, they're reading from databases. All of their modifications are going to journal files. And then we have a backup or an async system on the right that's going to be replicated. So the way this works is mirroring sends all of the journal data that's getting written to local journal files to each of the other mirror members, whether they're a backup or an async member. Those journal updates are acknowledged by the backup so that the primary knows what the backup has seen. And they're written to the backup or async's local copy of those mirror journal files. And then there's a process called dejournaling, where a few processes on the backup or async get involved in this dejournaling process, where they read journal data from the mirror journal files on the backup or async. They perform the same sets and kills that occurred in those journal files. They perform them on the backup or async's local copy of the databases. Okay. So this breaks down into basically three main interactions that need to be optimized. We'll go through each of these in detail in turn. The first is that for failover mirroring, some application events that we'll describe in a minute can wait for the backup to acknowledge receipt of data. Basically, there's some application events that want to make sure that data is durable. So on a local system, that means writing it to the local journal file, and but with failover mirroring, with an active backup member, it means both writing it to the local journal file and ensuring that the backup has received that data. There's of course just the raw journal. There's some throughput considerations in just the raw journal transfer, basically the transfer over the wire and writing to disk. And then there's the rate at which dejournaling can happen. So dejournaling on the backup or async system needs to be able to keep up with activity that's occurring on the primary, so that those systems are ready to become primary when the need arises. So let's take these in sequence. First, talk about journal synchronization events. So what is this? In general, what's happening here is, with a journal synchronization event, is that the application has done something and done some set of modifications to the database, and the application wants to ensure that that data is durable. And by durable, I don't necessarily mean durable in the journal file, in the database files, but durable in the journal files such that if the system were to crash, that data that the application just wrote is guaranteed to be recovered automatically. So it's durably committed to stable storage. So with no mirror, this is a thing in normal systems without mirroring at all. An application that requests one of these journal synchronization events will kick off an I/O to the journal files and then wait for that to be durably written to complete durably to the journal file. When failover mirroring is involved, the backups, a journal synchronization event also requires the backup to acknowledge that data. Purpose there is that if the primary were to fail and the backup takes over automatically, we need to make sure that the backup has seen that data and will recover it before becoming primary. So how do you do this? Application code can explicitly wait for data to become durable. This is with the synchronous commit transactions. So when you do a t-start, if your process is in the non-default synchronous commit mode, then that t-commit will trigger an I/O and wait for that journal I/O to complete. And will also wait for the backup to acknowledge receipt of that data. There's also a journal sync API documented in the class reference. Ensemble uses this too. When Ensemble takes in an HL7 message, for example, it'll persist that data durably. It'll persist that message durably in the Ensemble database before sending an acknowledgement to the sending system. And that, under the covers, that just uses synchronous commit transactions. ECP also uses this. And so if your mirror system is an ECP database server, in order to provide the ECP recoverability guarantees, certain events in ECP will have to wait for a local journal write and a mirror acknowledgement in order to, before it can provide an answer to a client, to an ECP client. So let's talk about what the factors are in optimizing this. The first thing is to recognize that many, maybe even most environments, this simply doesn't apply. Reasons it might not apply is most applications aren't using synchronous commit transactions, or certainly aren't using it enough that it becomes a performance sensitive thing. If you're not using, if you only have one failover member defined, if you're just using mirroring for asyncs, then this doesn't apply because asyncs are an asynchronous replication, and journal synchronization events simply don't wait for an acknowledgement from asyncs. They only wait for active backups. In environments where it does apply, really the main concern is network latency. So if you have your failover members in the same data center, maybe even in the same rack, sitting right next to each other, connected by a sub-millisecond latency network, there's really no issue. Basically, as long as the network latency is less than the local disk service time on the local journal disk, then you pay no extra cost for response time waiting for that mirror acknowledgement. SSL encryption and compression can also add a little bit of a computational latency, but it's relatively minor, especially when compared to network latencies. So what else do you do? Application parallelization becomes, if you're using synchronous commit, parallelization in the application becomes important. Imagine a 10 millisecond network round trip time. So one process, that means one process every time it does a synchronous commit has to wait 10 milliseconds to get the answer, because it's going to trigger a journal write to the backup and wait for the acknowledgement to come back. So if you have 10 milliseconds round trip time, you can wait 10 milliseconds 100 times per second, right? 10 milliseconds times 100 is 1 second. So that means that one process can only, in such an environment, one process could only commit 100 transactions per second in synchronous commit mode. However, if that same work was parallelized across multiple processes, you could get dozens or hundreds of processes all doing that 100 transactions per second, all in parallel over the same channel, because multiple synchronous commit, multiple transactions are going to be sent in the same packet to mirror and acknowledged in the same acknowledgement. So these do batch up. So although, so if an application uses this a lot and you're using failover mirroring across a distance, you'd want to review how your application works in terms of parallelization, that the number of synchronous commit requests don't exceed, per process, don't exceed the possibility, the limits imposed by the network round trip time. And failover members really need equally capable hardware, particularly journal disks, in order to keep up, and for other reasons that we'll cover in a little bit. We've done a little bit of work in the latest version of our product to make sure that if a backup member has hardware that has some kind of hardware hiccup, that it doesn't slow acknowledgments to the primary. But in general, the failover members really need to have equally capable hardware, primarily because the backup will become primary someday and have to serve the production users. So that's probably the most complicated of the three. Number two is just simply the raw network, the propagation of this journal data over the network and down to the disk on the backup or async, and how do we obtain optimal throughput there? Well, number one is basically to understand what your journal creation rate is, understand how much data is going to be going over that network. So just to give you a flavor of this, 300 gigabytes of journal per day is a pretty large system. It's not, not the biggest system in the world, but that's a pretty busy system. So let's just take that as an example. And let's say, it's kind of overestimating, but that's good. Let's say that 300 gigabytes of journal was all created in 8 or 9 normal business hours. Most systems that wouldn't be true, but that's okay. We kind of want to overestimate the throughput requirements. So that would mean that during the day, during those 9 hours, you're creating roughly 10 megabytes a second, or 80 megabits in network bandwidth terms. And then there's a little bit of a question, does this actually account enough for the burstiness of your application? If your application is one that's going to, at any point in time, suck in, someone's going to come along and randomly insert 4 gigabytes of data as fast as possible, maybe this actually doesn't account enough for bursts. But for transactional systems with more or less regular load, a calculation like this may very well account for bursts. If you have geographical separation, another consideration is bandwidth delay product. Bandwidth delay product is a sort of a well-understood networking thing. There's a very short Wikipedia page on it. You can catch up if you're interested. But basically, bandwidth delay product is sort of how many round trips can I get per second, and if I needed to sustain this 10 megabytes per second, I would need to be able to buffer enough data so that I can receive a TCP acknowledgement before I fill my buffer. So here's the calculation using my 10 megabyte per second example, and imagining two systems on the east and the west coast, which is about 100 milliseconds round trip time. That means in order to sustain 10 megabytes a second, I need to be able to put 100 megabytes, 1 megabyte on the wire without running out of TCP buffer. So we've done some work in 2016.1 that allows mirroring to use extremely high TCP buffer sizes to support these kind of extreme configurations where we have a fairly high journal creation rate and a very long round trip time. So if you're interested in that, you can take a look at the 2016.1 documentation. This is all described in more detail. Switching gears on throughput a little bit, we just recently in 2016.1 introduced gzip compression on the wire for mirror journal transfer. Compression we're finding that with sort of normal data, like a fair amount of text, some integers, some list build, that sort of stuff, compression can reduce bandwidth requirements by as much as 80%. And with, of course you can have even data that's even more compressible than that, but we're seeing 70 or 80% be a pretty conservative guess for normal text data. Obviously, if most of your data is like compressed JPEGs or something, you're not going to get any benefit from compression. There is a computational overhead that comes with this. It's a little bit interesting, actually. When we compare the overhead, the cost of that compression adds to latency, we find that it does add some, right? But if you compare compression with SSL encryption versus just SSL encryption alone, which is sort of what most people use when they configure a mirror, compression actually reduces the cost a little bit because the SSL encryption is actually pretty costly. So compression applies first, reduces the amount of data that needs to be SSL encrypted, and actually overall saves time. At least on our test hardware on Linux when we tested this a year ago. Certainly, your mileage will vary based on how compressible your data is, how efficient SSL encryption is on your particular chip. There's lots of factors that go into this. Both of these things, SSL encryption and compression, can limit throughput at the very high extreme end of ingestion. So if you had like a financial application that does nothing but pump data into the database as fast as possible, you may see that you pay a throughput cost by using SSL encryption or by using compression. So in certain extreme cases, you could think about removing both of those. We make this selectable for failover members and async members independently. Our defaults are that async members just always use compression because we figure async members are often in different data centers, going over not the best networks, and saving the bandwidth is useful. For failover members, our default is a little complicated in that if SSL encryption is not used, then failover members default to not using compression. And that's because compression introduces, like I mentioned, a computational latency that you would pay in those journal synchronization events. If, however, you were configured to use SSL encryption, then our default is that we use compression also for failover members because our testing has shown that compression actually reduces computational latency as compared to SSL encryption alone. So basically, the default for failover members is just optimized for journal synchronization performance. And the default for asyncs is optimized for network bandwidth. The last thing to say about journal throughput is basically that just based on your calculation of how much your journal creation rate, you need a disk on the backup or async that will support that. And again, with failover members, they simply need equally capable hardware. So the last of these is the dejournaling process that I mentioned. So dejournaling is a bit interesting in that you might have thousands of processes over there on the primary that are inserting, modifying data. But over here on the poor backup or async, he's got to read all these journal files and have some set of processes that does the equivalent of those the equivalent amount of database updates as those thousands of users over on the primary. Dejournaling also operates with just a single process doing all the updates. So there's a bunch of, you'll see if you ever run a mirror or even Dejournaling, you'll see a bunch of processes get started. So these processes are little helper guys, and they run around, they do prefetching, they try to prefetch database blocks in from the file up into global buffers on the backup or async, so that when the updater gets there, gets around to actually performing the set or kill, that it can go as fast as possible. But there's a reason why dejournaling uses one updater because we really want to preserve the order of updates that came from the journal file. So if you had multiple updaters, you'd worry that journal records get applied out of order, and what are the implications of that? We'll talk about that in a minute because that's something we're working on changing. So how do you optimize dejournal throughput? Well, these are just processes performing sets and kills like any other process. So all the normal database performance stuff comes into play. You want to make sure you have plenty of global buffers. You want to make sure that the disk subsystem is proper for a database, that it has good write throughput and great random read performance, because that's what databases do. We've done a lot of algorithmic improvements around that either directly or indirectly help dejournaling. So some of you may have seen that in 2015.2, we vastly increased the number of global vectors that a process has. You don't need to know much about global vectors, but basically every process caches some information about most recently used globals in these global vectors. And it was previously limited to 32. Global vectors are very important for dejournaling. They allow the dejournal process to work as fast as possible. And by having more of them, it actually helps dejournaling performance substantially in some environments. 2016.1 also has some algorithmic enhancements to improve block contention between the dejournal jobs themselves. And as I mentioned, one of our development projects that's ongoing is to